what does it mean to be normal? Am I normal? Perhaps not. But what about your data? Normality is a major assumption for many statistical analyses. But I'm here today to tell you why I think worrying about your data being normally distributed is overrated. But first, let's cover a few of the basics.
Many biological variables, when measured and plotted as a frequency distribution, form a bell shape. The normal distribution is a continuous probability distribution that describes a bell-shaped curve which can be used as an approximation of the frequency distribution. There are two parameters that are used to describe the shape of a normal distribution, and they are the mean and standard deviation, which describe the location and the spread of the curve, respectively. There are an infinite number of normal distributions, but they all share several properties. The values always range from negative infinity to positive infinity. Because these distributions are continuous, the probability is measured by the area under the curve rather than the height of the curve. Normal distributions are symmetric around the mean, have a single mode, and the mean is equal to the median and the mode. The probability density is highest at the mean, such that 68.3% of the area under the curve lies within one standard deviation of the mean, and 95% of the area under the curve lies within 1.96 standard deviations of the mean.
This is my best imitation of a normal distribution. I still don't think I'm normal.
The normal distribution can also be used to describe the sampling distribution of some estimates, including the mean. The sampling distribution of sample means is the distribution of means of all possible samples of size n taken from the population. When the variable being measured has a normal distribution in the population, then the distribution of sample means will also be normal. The mean of the distribution of sample means will equal the mean of the population, but the spread of the distribution will be smaller, such that the standard deviation of the means is less than the standard deviation of the parent population. If the variable being measured does not have a normal distribution in the population, the distribution of sample means will be more normal, and when sample size is large, the distribution of sample means will be approximately normal. This phenomenon is described by the Central Limit Theorem, which states that as sample size increases, the probability distribution of means of samples from any distribution will approach a normal distribution.
When you analyze your data using any kind of parametric linear model, one of the major assumptions is normality. I believe that most researchers are far too concerned about meeting this assumption. Most of these analyses are actually robust to departures from normality. Most often, you're testing hypotheses about means, so it's actually the distribution of the means that needs to be normal. But if you have designed your experiment well and you have sufficient sample size, then you don't have to worry if your variable comes from a non-normal distribution, because the distribution of the means will be more, if not approximately normal.
It is commonly a knee-jerk reaction to transform data that come from a non-normal distribution, but because of the central limit theorem, it is often not actually necessary. Of course, there are some exceptions or cases when data transformation may be required, for example, when a variable has a heavily skewed Poisson distribution. An important caveat to remember is that any results from statistics that are performed on transformed data are only applicable to the transformed version of the variable and should only be discussed as such. P-values do not hold for back-transformed values. This can often make discussing the results complicated and is one reason why it is not advantageous to transform your data if it is not needed. Unfortunately, even data transformation cannot fix the distribution of data that has few non-zero points. No matter what kind of transformation you attempt, they will always remain a peak in the distribution. In these cases, non-parametric data analyses could be performed, but even then all of the zero values will be assigned the same rank, so this is often still not particularly helpful. Other possible solutions are to look at the variable as binary, 0 versus non-zero, or compare the level of responses among instances where a non-zero response was measured.
What if I don't know what the distribution of my variable looks like? Is there a way for me to check it?
When your sample size is large, plotting and visually inspecting the frequency distribution of the data from your sample can give you an indication if your variable of interest tends to follow a normal distribution. Again, this is not the real assumption you need to meet. If the sample data do appear to form a normal distribution, that's ideal because then you know the distribution of sample means will also be normal. But if it does not, once again, it does not necessarily mean you need to transform your data because the Central Limit Theorem has got your back. It is important to note that if you have more than a single population or multiple treatments, and if those populations or treatments are different, you would not expect them to be normally distributed because all individuals' values would not be centered around the same mean. In this case, you would want to plot the data as their deviations from their predicted means. These deviations are otherwise known as residuals. There are some statistical tests available, such as the Shapiro-Wilk test, which will test the null hypothesis that the data follow a normal distribution. These tests are only valid if you have a sufficient sample size, and again, should be performed on the residuals. If you fail to reject the null hypothesis, you can feel very comfortable that you have met the normality assumption. But I will emphasize once again that even if these tests result in rejecting the null hypothesis, it only gives you information about the distribution of the variable in the parent population and not the distribution of the sample means, so it does not automatically indicate a need for data transformation.
So how do you feel about being normal now? Whatever, it's overrated. But you know what's not overrated? Subscribing to my channel. You know you want to. And if you're looking for some easy SAS codes to examine the assumption of normality for some of your sample data, check out my blog. There's a link in the video description below.